Welcome back to physics. Today we are going to start another topic called energy, work, and power. It obviously links with the topic we have just finished. You might have done a couple of things relating to energy last year in science. This topic will have a number of equations for us to learn. Don't worry, we'll be doing plenty of examples for you to get used to these equations. As usual, we always start with the topic checklist, where we have written all the subtopics that we will be learning in this topic. Okay, so we'll start off with page 23 and with our first question. What is energy? So the first thing we have is we are being told to give 3 examples of energy being used. Now, energy is being used constantly and we use energy all the time in every part of our lives. So if you are walking, you are using energy. If you are charging your device, you are using energy. If you are listening to this lesson, you are using energy through your device, through your computer or your tablet or your phone. So energy is all around us and it is being used all the time. Continuing on. Energy is all around us. All living things use energy in order to live, and machines use energy to do their function. When using energy, we say that we are doing work. Now, it is very important that when we refer to the term work, we do not mix this up with our common meaning of work, which is that of doing a job, cleaning dishes, doing your homework, or whatever job you have to do. This is, let's call it, a scientific work. Just like the time we referred to weight in our everyday life can sometimes mean something different than weight in science, in physics, work in this case is going to be the same thing. So work for science is not the same as work for our everyday lives. For example, when a person is pushing a box across the floor, he is using energy because he is moving the weight of the box. The person can be said to be doing work against the forces of weight and the force of friction present on the box. When going up the stairs, a person uses energy because they are doing work against the gravitational pull. This means that when doing work against a particular force, energy is being used. So that is why the definition for energy is the ability to do work. All objects that are able to do work possess some form of energy. The amount of work done is equal to the amount of energy transferred. Moving on to symbols and units. Since work is the amount of energy transferred, both work and energy are measured using the same unit, the joule. We've already talked a bit about the joule when we talked about specific heat capacity, and in this case, both work, as we shall see, and energy will be using the same unit. Like we had already mentioned, the joule is named after the British physicist James Prescott Joule, who did significant work in the field of energy. Here we have a table with the quantities of energy and work, and we are going to insert the symbols for each and the unit. So the first one, the symbol for energy is a capital E, and the symbol for work is a capital W. Now this is very important that we do not mix up this capital W with the capital W we use for weight. This will be very important later on when we get to the calculations. In both cases, we have said that the unit there is going to be the joule, which for short is written as a capital J. Now for work, the same will apply. So for work, the unit will be the joule. Now let's go into a bit more detail about work. If a man is pulling an object, the amount of work done depends on 2 things. The man does more work if he pulls the object with a larger force, or if he pulls the object over a longer distance. The work done therefore depends on the force and the distance moved in the direction of the force. This can be represented by the following equation. And here we meet our equation. So work is equal to the force multiplied by the distance moved in the direction of the force. This is very important. Work is equal to the force multiplied by the distance moved in the direction of the force. Now work, we said its symbol is a capital W, force, its symbol is a capital F, and distance, we had said at the beginning of the year, its symbol is a small s. The symbol for distance is a small s. The force F is measured in newtons, while the distance s is measured in meters. Meters, for short, is written as a small m, while newtons, for short, is written as a capital N. Note that often, although not always, the work is done against the weight of the object. It is very important that we do not mix up work with weight. Both of them have a capital W, but they are two very different things. Moving to page 25. Remember that in this case, F, the force, is calculated by W equals mg. The force, if it is the weight, will be calculated by using the equation we had learned at the beginning of the year, W equals mg. Since weight W is a force, then we can substitute weight for the force over there. Let me remind you, W is the weight, m is the mass, and g is the acceleration due to gravity, which at your level, I've said multiple times, we take to be 10 meters per second squared, unless it is stated differently in the question.